Hello. We're going to continue today on our discussion on paper recycling. And the topic for today is going to be dispersion of contaminants in recovered paper stock. So this actually is a section where, or a part of the operation where if we haven't been able to remove contaminants using screening or cleaning or washing or flotation, what we'll do is we'll say, okay, how else can we combat the quality problems that are going to occur if we leave these particles in our paper? Well, so the concept here, the strategy here, is that we're going to use some mechanical action and temperature, and that will, this mechanical action will break down these particles. And a number of good things can happen. One of them is that they're so small that they don't bother us as a consumer of the recycled paper. And another one is, even better, that they're detached from the fibers, and they're better able to be removed, maybe in a subsequent washing or flotation step. Okay, so let's go ahead and look at the definition of dispersion. So we're going to call it the use of mechanical action to decrease the particle size of contaminants and release the contaminants from the fiber surfaces. And below, what I'm showing is actually an exaggerated picture of what should happen during dispersion. On the left here, what we see is this paper right here has these large specks of black, maybe it's coating chips that have not been, that are very offensive to our eye. And then after we apply mechanical action, we can get paper where those large specks that are offensive have been broken down into smaller pieces. Now, this actually came out of a magazine, a vendor for a disperser unit. And I believe it's an exaggeration. And also, the other things I think about this one is that there was probably some kind of bleaching process and maybe perhaps even a washing or a cleaning process. Washing, or I'd be more exact, flotation process perhaps, to get rid of some of the ink that's been, some of the contaminants have been broken down. But this is the idea. This would be the perfect case scenario. Okay, so what are the kind of things that we're trying to break down? The contaminants that, that exist that can be offensive and large are things like inks, toners, coatings, chips of coating that have been unpulped, wax, blobs, let's call them, bitumen, varnish. Varnish is like a UV cured coatings, let's say, that's on the top of a magazine but still is attached to perhaps some printing on the surface of the magazine. Hot melts, which are adhesives used in boxes oftentimes. And then big chunks of glue and things like that. So all these kinds of contaminants, if we use mechanical action, we've got a chance to break them down. We're going to apply the mechanical action, but we're also going to be assisted by heating in many cases. And some of these contaminants that I list up above, they are softened in the range of 60 to 120 degrees. And each contaminant has a specific softening point characteristic of itself. And but this just gives you a range that if we do heat up to 100, we can start to soften some of these materials and actually make them more amenable to breakage during mechanical action. The other thing is that these contaminants typically can end up being large, and what we try to do, just to give you a kind of a gross ruler, is break them from above a 40 micron diameter size to below a 40 micron diameter size. And about 40 microns, depending on how good your eyesight is the cutoff between visible and subvisible size. So we're going to be trying to break these contaminants below 40 microns. Okay, there are two methods to do this dispersion, and one of them is disc dispersion. We'll talk about that first. And the other one is what's called kneading. And the two processes work a little differently. Same concept, but the mechanical actions are applied in a different manner. We'll contrast these two. So first, let's talk about disc dispersion. Okay, how does it work? Pulp at high consistency is passed between discs that have bars or teeth protruding from the surface. So if you're familiar with paper refining, it's similar type of equipment to that, except for the fact that we have a different purpose and we're going to run it in a slightly different way in order to break contaminants, rather than in typical refining before a paper machine, we're trying to increase the bonding ability of the fibers by flexibilizing, swelling the fibers, and fibrillating them. Here, we're just going to try and break down contaminants. So one of the discs with teeth rotates, and that causes intense shearing action on the fibers and the contaminants that exist between the gaps of the two discs. Okay. Now, disc dispersion is typically run at high consistency, about 30% consistency. So oftentimes we'll need some thickening equipment to get us to that consistency. The temperature, it can range, but an average temperature might be 95 degrees Celsius. So we're close to the boiling point of water. We're going to need to use steam in order to heat the pulp up to that temperature. The retention time, interestingly enough, the pulp might only spend 2 seconds between these discs, and that's a short time, and so we have to have a very intense action in that short time. The rotational speed of the discs, around 1500 RPM, which is relatively quick. The gap between the discs, 0.5 to 1.5 millimeters. So just to kind of get an idea, a hardwood fiber is about 1 millimeter. So if we had a hardwood fiber end to end, it could touch both of the teeth. Okay, and what we'll have actually between those teeth are flocks of high consistency pulp. So those will definitely be big enough to get pinched by the teeth. One thing that we need to talk about is the energy requirements. And for disc dispersion, we need about 1.6 to 4.0 horsepower days per ton. And this is one of the places where we have to spend some money to run disc dispersion. And if disc dispersion is not effective, it's not doing the job, it's not needed for your products, this is the reason, this energy requirement is the reason why you don't just run it just to run it, because it costs money to run. Among other things, there's other disadvantages to disc dispersion. We'll talk a little bit about them later. Okay, this is a disc disperser, and if you look at it, it's going to remind you of a refiner, if you've seen what a refiner looks like. Okay, let me get my pointer. So the feed pulp actually is going to come into the eye here. So here's our feed pulp, and that's at 30% consistency. And that pulp is going to follow this gap right here. Okay? And of course, these discs are circular discs. And in this case, we have a rotating shaft here. And that rotating shaft has teeth attached to it, and it might be hard to see, but the teeth are right here. Okay, so this disc is rotating at 1400 RPM per, let's say, and the teeth here are moving around, and they're coming very close to the teeth on another disc. Now the teeth on the other disc are, in this case, stationary. Okay, so we have stationary teeth here, so we're getting the teeth to teeth closing the gap. The pulp is trying to squeeze through here. The teeth kind of cut and rub and break contaminants and actually fibers also, unfortunately. And it's just a very quick action. 2 seconds in here, bang, and then the pulp leaves out the exit. Okay, so there's no rejects stream here. All the contaminants are broken up and still remain in the pulp. If we keep them there, they'll darken the pulp a little bit. If we go to a de-inking step or some type of cleaning or cleaning process, screening wouldn't work very well because we've broken this up into small particles. But If we go to an operation that removes a contaminant, then we might not have that problem of darkening our pulp. Okay, so I mentioned to you that dispersion actually, we run that on 30% consistency pulp. And so we've got to invest in some equipment to actually run this process. Here what we're doing is we're showing the equipment that's needed to dewater the pulp to 30% consistency. First what we'll do is we'll start off with a pulp around 3 to 5%, and that's going to, that pulp may have already run through a low consistency thickener. But then we'll take that from 3 to 5% pulp and we'll use a screw dewaterer. So we've got a screw and it's just pressing that pulp, and we've got a perforated cylindrical device here, and we're going to get our pulp to about 8 to 12% consistency. And then what we'll do is we'll have a screw press. Again, very similar. We've got a screw that's actually squeezing that pulp up against a plate around here, and again a perforated cylinder that allows the water to go through. And at that point, this is called the dewatering zone right here. At that point we're getting pulp consistency of about 28 to 30%. Okay, then the pulp actually comes down here and it goes into this screw right here. And this screw is actually used to break up clods of stock. So we want to break up big clumps of stock. So this press is going to press it up against the plate. We're going to get big amounts, large kind of blocks of the pulp. It'll come down here and it'll be broken up in this breaker screw. And then when it's broken down, and this is a picture right here of the pulp, maybe again hard to see, but the pulp's been kind of, the clods have been broken up. It will go down into a heating zone. And this heating zone is going to have some agitation here, and we will introduce steam into this pulp. Okay? And the clever thing is that we're adding the steam to the high consistency pulp, not the low consistency pulp, because we want to conserve our energy, and we don't want to be heating up water. We want to be heating up the fibers and the contaminants, which is our, well, we really want to just be heating up the contaminants, but the fibers must be heated up also. So we're in the heating zone here. We're heating up to, let's say, 85 to 120 degrees Celsius with steam. If we go above 120 degrees Celsius, yes, we will soften the contaminants more, but we will also potentially damage the fibers. So the integral strength of the individual fibers might be compromised because of chemical reactions that occur above 120 degrees Celsius. Okay, so then what happens next is the heated pulp from this heating zone right here will fall down into a feed screw, and that feed screw is going to push that in to right here, our disc disperser. So we've got our disc disperser here, and then the outlet of the pulp comes this way. And what we're looking at is a pretty big motor right here to run that disc disperser. And so our outlet pulp's going to be 30%. And this is a typo down here. I don't even think you can see it, but the outlet consistency is about 30%. The pulp may be diluted and agitated for further processing, so that's going to be a next step. All right, what I want to do is kind of just show you some equipment here. This is a screw press from a, actually it's an ONP mill, I believe. ONP or OCC, I believe it's OCC actually. And what happens here is we've got a feed chute, and the pulp comes down here, and the screw is in here, and there's a, and then looking in this insert here, this right here, we open up one of these things, and we can actually see the perforated, it's hard to see the perforated cylinder, but you can look and see the water dripping out of the screw press. So prior to this, the pulp was probably thickened using a disc filter or some kind of gravity decker. Now after that screw press, what happens is that pulp falls down into the heating zone. And this is the heating zone right here. And remember, it had like a rod in the middle with paddles that kind of agitated the pulp. And then these lines right here, as you can tell, is steam. And so the steam is added here, and in this case it's 35-pound steam. And so the 35-pound steam is added across this heating zone, and good agitation will heat up the pulp and soften the contaminants. Okay, so after that, here's that heating zone. Then after the heating zone, the pulp falls down into this screw conveyor, and the screw conveyor actually forces it into the disperser. And the disperser is kind of hard to see here, but this thing right here is the disperser. In this inset right here, we can see the refiner right here. Okay, so here's the refiner. And what we have here is a motor, but we've got a special kind of motor. It's an ABM motor. An ABM motor, an awfully big motor. So we've got to spend a lot of money actually to turn this rod and actually run the disperser. Okay, so that's disc dispersion. To kind of just review disc dispersion, we use intense mechanical action. We have to heat the pulp up. The pulp's at high consistency, and it passes through these close gap teeth. Unfortunate thing about disc dispersion is that it does cut a lot of fibers, and so that cutting action can be a problem if strength is an issue or runnability on your paper machine. So there's an alternative, a little bit more gentler alternative. Let's go to the next slide, and that's called kneading. I like to think about dispersion and kneading like this. Dispersion is like if you went to go get a massage and the masseuse would be banging your back with their fist, just smashing you, and it takes 5 seconds, but they punch you out, basically. Now kneading is the kind of massage that you would like. It's going to be a slower, gentler, easier to kind of relax and enjoy kind of massage. So let's just kind of see how kneading works. What we're going to do is we're going to take pulp at high consistency and mix this pulp and shear it between moving bars on a slow rotating shaft and stationary bars attached to the housing. Okay? And the strong shear forces that we create from these moving bars is going to cause a lot of, mainly, now in this case, fiber to fiber rubbing, which breaks the contaminants. And I should mention that with the disc dispersion, most of the action occurs because the teeth actually hit the contaminants, or the teeth actually hit the fibers. In kneading, that's not the case. It's more fiber-fiber rubbing. Okay, so the typical conditions, we're looking at consistencies, again, around 30% K. Temperatures, in many cases, we don't use as high a temperature, so 40 to 50 degrees Celsius is typical for kneading. Now the retention time, 10 to 60 seconds. So if we think back to disc dispersion, it was more like 2 seconds. RPM ranges around 500, 600 RPM. A little bit slower, maybe half the speed as the disc dispersion. The gap between the bars, 10 to 40 millimeters. Recall, disc dispersion was 1 millimeter. Remember I mentioned that a hardwood fiber could actually cross the gap. 10 to 40 millimeters, well, we would need 10 to 40 hardwood fibers to cross that gap. So you see that the actual moving bars here are not going to impact as many fibers, the percentage of fibers that the disc disperser was going to. And then the last thing on the bottom is the energy consumption. And the energy consumption is 3.0 to 4.5 horsepower days per ton. So that is very important factor. So it's quite energy consumptive. Okay, so let's go ahead and we'll look at a diagram of a single shaft kneader. Okay, so previous to the pulp coming into our system here, we've already thickened our stock to 30%. So again, it might be a gravity decker and some type of screw press, perhaps. The stock enters the feed screw portion down here, and the pulp will come in here, and then the screw is actually going to push that pulp in towards the kneading section. Okay. Now, in this feed screw, I should mention that oftentimes steam might be added, or even a bleaching chemical like peroxide is added. And the reason why is because we've got we've got some pretty good retention time here at high consistency, and that bleaching chemical will you don't want to do bleaching at low consistency because you're diluting your active chemical bleaching agent. And so this is a nice place where you have good mixing, some retention time, high consistency stock, and it's a nice place to do maybe some bleaching. Okay, so the stock is actually kneaded in this region right here. And what this is showing is we've got our shaft, and these things are teeth. So these are teeth, and they might be 6 inches long. And we can see some other teeth here. So here's a tooth on the shaft. And then we also have some teeth that are attached to the housing. So these teeth right here, this one, and this one, and this one, and this one, these are stationary, remain on the housing. And so what happens is the pulp comes in, and then the pulp is between these the moving and the stationary teeth, and the pulp, it just gets kneaded. It's a good way of putting it. And the fiber rubbing that occurs actually is breaking the contaminants. And that's an important point. It's the fiber rubbing, not the metal to contaminant. In kneading, fiber rubbing does the breaking. In disc dispersion, metal teeth contacting contaminants does the breaking. So here we're getting fiber rubbing. That's why when I use my analogy of the massage, what we're getting is a much slower, softer, gentler mechanical action as opposed to the disc disperser. Okay. All right, that was a single shaft kneader, and we also can have double shaft kneaders. And it's the same as a single shaft kneader, except we've got two shafts now, and the shafts are rotating, and oftentimes they're always rotating in different directions. So here, up here on this diagram, we've got one shaft that's rotating in a clockwise fashion, and then this shaft is rotating at a counterclockwise fashion. Okay, and the other, so that's going to cause in this area some significant shear action. And then the other thing that's done is that one of the shafts is usually rotating at a different rotational speed than the other shaft. So this one might be moving 20% faster or slower than this shaft. And that'll also improve the movement of the pulp and the shear action. So we get some intense shearing action. Now this is a picture of the kneader with the lid off. So the lid has been taken off. This might be a case for when we have some maintenance issues and we have to take the lid off. So the lid is taken off, and you can see the two shafts, and you can see the teeth. Okay, and these teeth are large. They're 6, 8 inches sometimes. Okay, now this cartoon is nice also because it kind of shows a lot of the different parts. This is the feed right here, and the pulp falls down in, and you can see the two screws that are attached to the shafts. They will push that pulp into the kneading zone. Excuse me. And here are our kneading shafts with our teeth, and the teeth are moving in a counter motion type of direction, one clockwise, one counterclockwise. and then the pulp is going to fall out somewhere here, which we don't see. Here's the kneader with the lid on down here. So the pulp falls down through here, it gets kneaded through here with the lid on, and then the accepts kind of fall out the bottom down here. Okay, so some drawbacks to kneading. It's pretty energy intensive, 3 to 4.5 horsepower days per ton. You don't run this unless there's a need. I'm very familiar with kneading of mixed office waste or printing and writing grades that are going to be recycled and used for use in copy paper. So one of the mills that I'm familiar with uses kneading actually to break down toner and coating particles and large ink particles, let's say, breaks all those down and then actually dilutes the pulp and goes into another flotation cell, and also does bleaching in there. And then that pulp is used as it's mixed in with virgin fiber to make copy paper. There is a very high initial capital cost to put in a kneading system. So if you have a recycling system and you want to think about putting in kneading or disc dispersion, both of them have high initial capital costs. And part of the reason is because you've got to invest in the thickening equipment that has to occur before the dispersion. So yeah, that's why this next bullet requires thickening equipment. That's a capital issue, and then it's also a maintenance issue. Kneading doesn't typically reduce sticky size, and this may be an advantage because sometimes it's better to have the stickies large than small. If we have the stickies larger, it's easier to screen them, and screening actually is one of the more effective ways to remove stickies. So it does not reduce stickies. And then the rotors can wear out. So every 1 or 2 years you have to replace your rotors, your teeth, because of all that shear action and the abrasive material that's in the pulp. Every 1 or 2 years you have to replace your rotors, and that can be expensive. Disc dispersers, you also have to replace those discs, but the discs aren't as expensive, but they may wear out a little bit faster because of the faster speeds and the closer clearances of the teeth. Okay, so now I just kind of want to summarize and contrast kneading versus dispersion. Okay, these are both methods to decrease contaminant size. Okay, so for dispersion, what we're going to say is we're going to use some shearing action, and really the other thing that I should have put there is there's a lot of metal to contaminant contact. For kneading, we're going to get a rubbing. So it's rubbing, and it's really fiber to fiber rubbing. It's not the metal to contaminant rubbing. So what happens for kneading is that there's a contaminant. It's in between fibers. The fibers rub the contaminant and break it. Both have high consistencies. The temperature of kneading is usually lower than the temperature for dispersion. As I said before, kneading is a slower, more gentler massage. It's going to have a lower RPM, and it's going to have a higher retention time. So adding bleaching chemical in the kneader is a very common practice. And then, of course, the gap. The gap between teeth and the disc disperser about 1 millimeter, and the gap between teeth, let's say, or bars, is about 10 to 40 millimeters in kneading. So what that tells you is that in kneading, we're going to depend on the fibers to actually, fiber-fiber rubbing to do the mechanical action, actually impact the contaminants. And that's not the case in dispersion. In dispersion, with that small gap, it's pretty likely that the metal teeth will impact the contaminant. Okay, so again, some more comparison, some of the effectiveness, pluses and minuses of kneading and dispersion. One study shows that disc dispersion is going to break down tappy dirt 75%. So tappy dirt is visible dirt. So tappy dirt measures visible dirt. And so the dispersion can actually reduce that visible dirt by 75%. It might lower our brightness of our pulp, but we understand that. And kneading, 85%, so a little bit more effective. Toner reduction, yes, dispersion will work. Kneading is actually better. So we get a better efficiency in toner breakdown with the kneader. Stickies reduction, the disperser actually does a better job here because of the intense metal to contaminant contact action. So stickies reduction is better for dispersion. Kneading, many studies have shown no effect, but that's kind of controversial. And like we said, stickies reduction, when I say better for dispersion, what I mean is that there's more reduction that's occurring. It may not necessarily be better. If your mill doesn't have a stickies problem and you just want to remove the offensive look of the stickies, then you'd want disc dispersion. But if you want to keep your stickies large and screen them out, you'd want to use kneading. Fiber cutting. I didn't stress this, but I should mention it now and make a good, clear point about this. In disc dispersion, that gap's 1 millimeter. So let's say if you have a softwood fiber that's 3 millimeters long. There are pretty good chances that that fiber is going to see the metal teeth, and it may even get cut. And fiber cutting is substantial for dispersion. So that is a drawback. So if strength and drainage on your paper machine is an issue, dispersion can be accentuate that problem. Kneading, on the other hand, it says no fiber cutting, but that's probably not 100% true. There's probably some fiber breaking, let's call it, but it's insignificant compared to dispersion. So for kneading, there's very little fiber cutting. And I guess this is a good point. Dispersion is very common in use with, let's say, OCC, old corrugated container grades, and ONP, old newsprint grades. And if you think about them, those are fibers that have the lignin in them. They're pretty, the fiber itself is strong. So that's an issue. The dispersion we can get away with dispersion with ONP and OCC because of the inherent strength of those individual fibers that have lignin in them. Now, in contrast, kneading is often used in mixed office waste. If you think about mixed office waste, that mixed office waste typically has a lot of chemically bleached hardwood fibers. And those chemically bleached hardwood fibers are very susceptible to damage. And if we're so if we're going to try to break down the contaminants in there, we want to make sure that we don't hurt our fibers. So chemically bleached pulps, like mixed office waste, often contains quite a bit of. We want to use kneading because it's more gentle and we will not break as many of the fibers. Fines generation just kind of follows that fiber cutting. So we're going to generate some fines in disc dispersion, but in kneading we're not going to generate as many fines because of the more gentler action of the fiber-fiber rubbing rather than the metal to contaminant or metal to fiber action. So just as a review, let's just kind of do an exercise. I've got a cartoon that kind of portrays the two processes, disc dispersion and kneading. So here we have over here, we're showing two solid objects. I won't say if they're teeth or bars, but the big hint here is that we've got a gap. It's about 1 millimeter. So that suggests that we have, this is going to be our disc disperser. On this cartoon right here, we've got our bars, let's call them, and the bars are separated by a gap of 10 to 40 millimeters. Okay, so I'm actually going to go way out on a limb and say that this is going to be our kneading operation. Okay, so first let's run the, this operation here on the left, and I'll hit the play animation button. And what happens, you notice that the teeth actually come into contact with the contaminant particle. If you think about it, it's not very unusual to have a contaminant particle, something like a chip of coating material or adhesive or maybe a varnish or a hot melt. They can be very reasonable to think that they're going to be around 0.5 millimeter to 1 millimeter, or 1.5 millimeter, or much larger. So we can see that this animation is kind of accurate in the fact that we're seeing a contaminant that's actually about 1 millimeter, and the motion of the teeth are directly impacting that contaminant and breaking it. So very reasonable right there. Okay, now let's run the kneading. And what we know already, we've got a 10 to 40 millimeter gap. Let's think about it. Wax particles, coated chips that have gotten all the way through the recycling process. They've gone through probably some pressure screens. They're going to be much less than 40 millimeters or 4 centimeters or about 2 inches, right? This is about a 2-inch gap. So we would expect that there's not going to be a contaminant big enough to kind of cross this gap here. So let's just see what happens with this one. So we notice a couple things that are occurring here. First of all, this bar at the top is moving a lot slower than when this tooth right here was moving. So we notice that our motion is about half the speed of the disc disperser. And then the other thing we notice is our contaminant is actually in the middle of both of those bars, and it never really touches those metal bars at all, does it? But what I'm also showing here is that there's that flock of yellow, in this case I put yellow, yellow fibers. And it's actually that flock of yellow fibers that's actually applying the mechanical action to the contaminants. So we see here that kneading is a much slower, gentler, fiber-to-fiber rubbing of the fibers. And you can see that the fibers, and I might not have the size scale all perfect and everything, but there are going to be very few fibers that are going to be cut or pinched, let's call it pinched, between the bars. There's usually going to be several layers of fibers, and each layer will rub against the next layer, and there'll be several layers between the two bars. So again, one last time, disc dispersion pretty quick, kneading pretty slow, and using that fiber to impart the mechanical action. So just kind of to review, what we've talked about are 2 different methods that we can use to break down contaminants to subvisible size. Now the other thing that we can do with these methods of applying mechanical action is to actually, in many cases, we detach them from the fiber and make them smaller, so that both of these things, detachment of the fiber and the small size, will allow washing or flotation to be more effective. So if we have the ability to have a de-inking process after dispersing or after kneading, then we can take advantage of, maybe we've separated some of the inks from the fibers, and maybe we've made them smaller so that they're more amenable to washing or flotation. The drawbacks of kneading and dispersion. They both are energy intensive, so it costs money to run the motors to run the disperser or kneader. So they're costly. The other thing is that there's capital equipment that needs to be purchased for them, thickening and the actual kneading or dispersion, and maintenance can be an issue. You've got to maintain all the washer, the thickener, the heating zone, all this stuff, and so maintenance is another issue. And then finally, we can talk about fiber cutting. With disc dispersion, this can be an issue. We can degrade the fiber quality, and if we overdo it, we'll have very weak pulp that will not drain very well on the paper machine. Kneading is not as hard on the fibers because of the slower rubbing action, and that's why kneading is used in mixed office waste and other chemically pulped and bleached fibers that are very susceptible to fiber damage. And that will conclude my presentation on kneading and dispersion.